Okay, my name's Andy Davis. I'm Research Director of NCC Group, and I'm going to be talking today about some of the research I've done into USB and identifying systems purely by the communications over the USB stack. So the talk's split into two separate sections. First of all, I'll be talking about the kind of primary stuff, which is enumerating information from a system via USB. And the second part is going to be concentrating on a Windows bug that I discovered earlier on in the year, which has now been fixed, but as per usual, Microsoft didn't actually reveal too many details about where the flaw was when the patch came out, so we're talking a bit through that. So first of all, information gathering. So why do we care? Okay, yeah, we may well be able to identify information about a target system via USB, but if we're physically connected to it, surely we know what that system is anyway. Well, that's not necessarily the case. Certainly with embedded systems, more and more we're getting to test devices that are part of automotive systems, SCADA type systems, where we may be just provided with a black box that's got a whole bunch of interfaces, one of which may be USB. And we want to gather as much information about what the system is within that box to enable us to test it much more effectively and much more in a much more streamlined way. As you'll see, when you're testing USB, it's a much slower process than if you're testing something like a network stack. So to be able to really focus your testing in the right area saves you an awful lot of time. So a little bit about USB to start with. I'm not going to go through the whole details of how USB works, the ins and outs. That's been covered to death, and there's plenty of white papers and books that will explain USB. But just a few things that you need to know that will help to understand what this talk is all about. So the majority of the information that I'm gathering via USB is during the enumeration phase. So enumeration is the process that occurs when you insert a USB device into a host. So initially the host knows absolutely nothing about the device. So during enumeration, the host queries the device to gain as much information as possible about things like how fast that device communicates. There's a whole bunch of different speeds that can be used for USB devices depending on which version that they use. How much power is going to be consumed by the device. So you can either have bus-powered devices or self-powered devices. So if it's going to be bus-powered, how much power is it going to consume from the host? And there's the device needs to explain how many different configuration options it has. If, for example, you've got a multifunction device like a printer, scanner, that kind of thing, there are different configurations within USB that explain the capabilities of the device for each of those functions. All of this happens during this enumeration phase that happens over a period of seconds before you can start using the device. So plenty of information exchange goes on, and this is implemented in lots of different ways depending on the USB stack within the host that you're plugging the device into. One thing that's really important to remember about what we're trying to achieve here is the fundamental way that USB works is a master-slave environment. So the host is always the master and the device is the slave. So if us as a virtual device are trying to gain information about the host, we can't just query the host during this enumeration phase. That's not the way it works. It's the host that will query the device, and based on our responses as a device, we then look for follow-up responses, how they may change, that kind of thing, to then infer information about the host. So here's an example of a typical enumeration phase. The arrows at the beginning here are just indicating the direction of the traffic. So for example, when a host asks for a device descriptor from a device, the device descriptor is being sent from device to host. Host then sets an address. The device descriptor is requested a second time. I'll explain why in a minute. And then there's a bunch of different other descriptors that are requested to gain information about the device in order for the host to be able to load the appropriate drivers, configure the host driver configuration, and get the communication going with the USB device. So there are a number of peculiarities with this enumeration phase. You notice that the device descriptor was requested twice. What's happening there is initially when you plug in a device, I said that the host doesn't know anything about it, and it hasn't been assigned an address, so by default it will use address 0 on first insert. After the host has decided on an address that it will use to communicate with the device, it sets that device and then starts the whole process again. So it resets the device but with that new address. So requests that device descriptor the second time. There are also multiple requests for the same descriptor through the enumeration phase that you saw there. And this happens because different layers within the USB stack may request the same information. So we'll talk about the different elements of the typical USB stack shortly, but that same information is required multiple times by multiple components. Sometimes you see class-specific descriptors. You don't normally get class-specific communication with a device until the point at which enumeration is complete and the host knows what kind of device it is and has loaded the appropriate class drivers. However, there are some specific class types like hubs and HIDs, so human interface devices, things like mice and keyboards, that have specific descriptors that are exchanged during the enumeration phase. So I mentioned about different stack implementations. We'll look at a few examples. I'm not going to go into a great amount of detail here. I just want to raise a few issues, a few components within these that are important to what we're trying to achieve. So the host controller is the kind of lowest level element of USB. It's normally implemented in hardware because it's enforcing some of the areas of the spec that are very kind of hardware dependent, so voltage levels, timing, that kind of stuff. Above them, the host controller, you'll have the host controller driver, which provides this hardware abstraction layer to the USB driver, which is kind of like the core component within the host that performs the enumeration that we just talked about and understands how to pass off information to the appropriate class drivers. Above then, you have the specific class drivers, so for example, a mass storage driver, printer driver, that kind of thing. And then above there, the application software. So for example, if you plug in a USB camera, quite often application software will automatically be spawned to display images that are stored on the camera. But that application software is still communicating with components within the USB stack, so it's still considered part of it. So, yeah, a few high-level diagrams of USB driver stacks, just so that I can talk about a few different components. You can see there are a number of different host controllers here, things like OHCI, HCI's host controller interface. So there's a lot of different components to provide compatibility with older versions and slower implementations of USB. So OHCI, Open Host Controller Interface, is one of the older ones. Then there's an enhanced one, universal one, getting faster and faster, up to USB 3, which super speed USB, the extensible host controller interface. You'll notice a split between user mode and kernel mode. Traditionally, a lot of the driver components for the USB host stack are within kernel mode. And therefore, any vulnerabilities that are triggered within USB, like the one that I'll be describing later on in the talk, are in kernel mode and therefore provide the possibility for privilege escalation. More and more operating system designers are trying to get components out of the kernel into user land. So within Windows, more recently in Windows 8, more of the driver components have been moved into user mode. Linux USB stack, again, you can see the different host controller interfaces there. And another example, just an embedded access USB stack. So you can see the different layers and the different like class components, that kind of thing. So, but as I said, I'm not going to go into those in too much detail. So if we're going to try and identify information about these systems via USB, we need to be able to interact with it. And how are we going to do that? And what kind of areas of functionality do we need to be able to achieve with USB? Well, we clearly need to be able to capture USB traffic and be able to replay it faithfully. We need to have complete full control of any traffic that we generate. We don't want to be constrained by the rules laid down within the USB spec, because a lot of the techniques that we might want to do may fall well outside the USB spec. So we need complete control of every bit that we send. The ability to decode separate USB classes is very useful indeed. So there are separate specification documents for all the different USB classes and the class-specific traffic associated with them. So with our system that we're using, if we've got something that will automatically decode that so that we don't need to go through and read the spec every time we're trying to work out what's going on, that's really useful. Support for all the different speeds that are provided by USB. USB 2 and below, which is probably what most people are most familiar with, I've got low, high and full speed configurations, so the ability to replicate those is cool. USB 3 would be a bonus. I haven't focused any research on USB 3 yet, but it's something that I'm planning on looking at in the future. So if you've got money to spend, the gold-plated solution is using commercial test equipment that will allow you to capture and replay stuff. This MQP box is one of the boxes that I've been using. It's a very, very, very capable box, despite looking quite amateur in its construction. I haven't managed to find $20,000 to get one of these boxes, but I don't need to. The other box is perfectly fine. Much cheaper approach is using Travis Goodspeed's excellent face dancer board. Now, face dancer, as you may well have seen in other demonstrations, allows you to create virtualized USB devices using Python, and this it provides the framework of a lot of the research that I've done. And the best solution is actually to use both. So to use a face dancer to actually generate the traffic, but then because you're looking at in detail at the traffic that's coming back, you need to be able to capture, decode the classes, and interpret the data using the commercial USB sniffer. Another thing that's quite interesting is that that packet master device records data down to the microsecond level. And you, as well as seeing all the packet data, you see everything timed down to the microsecond, which is interesting in a specific case that I'll talk about later. And as I said, the class-specific data is decoded for you, so you don't need to constantly read the specs. So, enumerating information. The target list wasn't in any way carefully thought out. It was the machines that I had available to me in my lab. I was just initially interested to find out if there were any differences in the way that these stacks processed USB information during the enumeration phase and during class-specific communication. So, as I said, the whole master-slave setup means that to try and identify information about the host, you need to be responding to questions it asks you, and by the way you respond, prompt it to ask other questions. Because the first thing that we want to be able to do, if we're comprehensively testing a system, as well as identifying what the OS is to work out what drivers are supported, what class drivers are supported. Quite often in operating systems, a bunch of standard classes would be supported. So in Linux, for example, there's often a mass storage class, there's a HID class to control keyboard and mice, that kind of thing. And then there are more specific classes that you have to install separately. So if you've got an embedded system, a box that you've plugged into, before you start trying to work out if there are any particular implementation flaws, bugs within the way that the USB drivers have been implemented, you need to work out which ones you can test. So we need to enumerate the installed drivers and ideally try and identify if there are any other devices that are already connected. So you may well have other devices connected internally via the USB bus. So if we can identify those as well, that'll be very useful. So identifying class type information, where's that stored? Well, I talked about these descriptors that are being communicated by the device to the host during the enumeration phase. Here's a couple of examples. A device descriptor, which is what was sent at the very beginning of enumeration. That's just a section of the device descriptor there. And with some classes of device, they specify the device class within that device descriptor. The more common approach is, because you may have multiple interfaces on a USB device that support different classes, you will have the class-specific data in the actual interface descriptor, as you can see there. So you've got the interface class, the kind of high-level class. Is this a mass storage device, a printer, an image, audio, that kind of thing? You've then got subclass, which provides more detailed information, and then the kind of low-level protocol, what kind of protocol is being used. So when you think about it, it's actually a massive attack surface that is quite often completely untested on these types of device. Although there are only about 12 or 13 high-level USB classes, there are lots and lots of subclasses and lots of protocols for each of those. So, as I said, provides a massive attack surface from a fuzzing perspective. When you're talking about specific device drivers that have been installed rather than the generic ones that are available, those are indexed via the vendor ID and product ID, which are these 2-byte values which are provided in the device descriptor. So the vendor ID and the product ID basically map to the class driver. So once enumeration has finished, it then loads that driver, and you know that class communication can occur. These can potentially be brute forced if you want to try and identify when the class communication starts. So although if you're actually going through every combination of PID and VID, that's going to take you a huge amount of time. There's a published list of all the valid VIDs and PIDs. But I've got some ideas about shortcuts of enumerating those, but that's still work in progress at the moment. So how do we tell whether device drivers are actually installed or not? Well, just looking at the enumeration process, at the end of supplying all the information, the host will send a set configuration command based on the configurations that have been supplied. And if there's no communication past that point, then there isn't a driver installed for that class of device. So going back to what I was saying, the host is asking you what kind of device you are within your emulated device. You could say, you know, I'm a mass storage device, and it continues through, says set configuration. But if the host then doesn't start asking you questions based on that class, you know that class driver isn't installed. I talked about some other connected devices. If you sniff the USB bus, anything that's connected to the same host controller interface that you are connected to externally. So if that USB port that you're connected to on the outside is on the same bus as any internally connected USB devices, you'll see other traffic associated with those. And an idea that I've got, as well as information that you could glean purely by sniffing the traffic, because the face dancer board allows you to emulate a USB host as well as a USB device, potentially you could start requesting descriptors from other devices and gain information about those internally. So what kind of fingerprinting techniques can we use? Well, looking at the patterns of the way the descriptors are requested, timing information, what types of descriptor are requested. If we send invalid data in the responses, how does it kind of respond with further questions? And the order of the descriptor requests. So here's an example of some class-specific communication. So we've got this Linux-based TV set-top box and Windows 8. And you plug in your mass storage device, it goes through enumeration, and the way that these requests and replies happen are always the same every time you plug it in. So you can see straight away that different elements of the mass storage USB protocol are being used to identify information about the mass storage device before it can be used by the OS. So it's kind of gone through enumeration, it knows it's a mass storage device, the mass storage class driver is then kind of providing information. So you can immediately see there's a big difference in the way that those two host implementations deal with mass storage devices. Application identification. So I talked about these applications that pop up when you insert a USB device like a camera. So within Linux, you've got this pattern of requests and replies with the image class traffic. The Photos Metro app in Windows 8 works in a different way. Initially it asks for the device info in the same way, but then it decides to set a property value on one of the thumbnails, and within the property that it wants to set, it actually specifies exact details about the class driver that's installed within Windows 8. So having a look through the different platforms that I was testing, you can see that there are unique elements in the way that the different host stacks responded and communicated during either enumeration or within class-specific information. Now I mentioned about timing and the fact that you can time interactions on the USB stack down to the microsecond using that Packet Master test equipment. So this is something, again, that I'm still working on. A lot of this is still work in progress. You can see I've done 5 different captures of the enumeration phase associated with a specific device. So there's a huge amount of variance over the entire enumeration phase. It typically takes around kind of 5 or 6 seconds to go from initial device insertion to the point where class-specific communications occurring. But if you tie it down to the timing between specific elements within that enumeration phase, so here I've looked at the difference between the timing of request for string descriptor 0 and string descriptor 2, you're talking of a difference of 1 or 2 microseconds. So if we can tell that down to that kind of level of granularity, and we know what the OS is, maybe from one of the other techniques, maybe we can determine some information about the processor speed or about the speed of some of the bus technology within USB to provide more information about the target system. There are some operating system specific descriptors that are used, and some that are not necessarily specific to the OS, but are predominantly used by some OSs and not by others. So again, this can be used from an identification perspective if you see those occur during the enumeration phase. Now, responses to invalid data. This can be used for as part of our enumeration and fingerprinting, but also can be used for fuzzing to try and identify bugs within the parsing of this data. But what I've seen is different host implementations respond to invalid data in different ways. So if you look at the type of data that's provided within those descriptors, you've got length fields, you've got values that could have minimum and maximum values, you've got the ability to put logically incorrect information in there, missing data. So in some cases you get crashes, and from a fuzzing perspective that's great because you're identifying bugs. But other times you'll just get unique behavior, which is obviously what we're looking for when we're trying to fingerprint systems. So as an example, on Windows, any version of Windows, well I say any version after XP does this, but up to the current version, if you send a specifically logically incorrect HID report descriptor, so one of those descriptors that's sent in the initial enumeration phase but contains data about the configuration of the USB device, if you send a logically incorrect report descriptor, this happens. Obviously not very useful if you're trying to fingerprint the system, but from a identifying bugs perspective, pretty cool. So some USB stacks request that data in different order. You might get additional descriptors that are requested multiple times by different layers of the stack. So all in all, there's plenty of information that you can gain that will help you identify A, what the operating system is running on the device, and B, what device drivers are installed that you could then query and potentially fuzz. So I've written a tool called UMAP, which is very alpha, and I will be releasing this once I've tidied it up, but it's not really in a fit state to go public yet. But in a couple of months' time, this will go live on our GitHub repository. So let's go for a live demo. So just to explain, I'm connected to a face dancer board here via the host system, connected to a laptop here running Linux. So first of all, if I do minus capital L, and I'll list all the different device classes. So first of all, I want to find out an idea about what kind of device classes are supported by this device. So if I say, let's check to see if it supports the audio class. So it's not super quick. Like I said, it takes about kind of 5 to 6 seconds per enumeration emulation. So you're emulating the process of physically inserting and removing a USB device here. And so you can see That's the audio class, that's the subclass, and that's the protocol. And you can see that none of those are supported on this particular USB stack. Whereas if I go for 3 image class, that particular class of USB driver is installed on the target system. So if, for example, we were going to start fuzzing this, there would be no point in trying to fuzz the audio class because the drivers aren't installed. So we could focus on the image class. Another bit that you can do with UMAP is if, for example, you've seen VID and PID, the vendor ID and product ID numbers in the captured traffic, and you want to decode those. I mentioned that there's a publicly available list of all the registered VIDs and PIDs. So the tool downloads that and maintains a local copy of that, and you can do a lookup. So for example, so that's VID and PID. And so vendors, Dragon Rise Inc., and the product IDs for a gamepad. It provides the capability to do, using a number of those different techniques that I talked about for operating system identification, it will go through and try and work out what the connected system is. At the moment, it's primarily using the order of both class-specific and enumeration-specific information. It's told us that it's Linux. If you want to specifically emulate a device, so let's say I want to just pretend to be an image class device, I can say just be an image class. So where's I need to provide the VID, the PID, and another element called revision, which isn't particularly important, but I can just make these up and it will still work. And you'll see the communication. So that's all the initial enumeration phase and then the class-specific data between my host and the target system. So to the target system, it's seeing that I've plugged in a camera, a USB camera. And I've mentioned fuzzing a couple of times. I've done quite a bit of USB fuzzing in the past, and this new capability that FaceDancer has allowed me to have provides the capability to do much more comprehensive fuzzing now. So you identify what classes are supported, and then you can fuzz based on, rather than mutation-based fuzzing that I've done in the past, you can look at the spec and implement all your fuzz test cases based on the spec for the class of device that you want to fuzz. So we've got a bunch of test cases that are kind of class independent, and then there's a whole bunch of image class ones based on that PIMA 15740 spec. So it goes through and you can fuzz all that lot. So if I do minus F3, it will go through and for each test case, emulating the process of inserting and removing a device with each of the components within the spec modified based on the test cases that I've got. But that will go for quite a long time, so I'll stop that. Okay. So just a bit of an overview of what you can currently do with UMAP. You can identify the device classes that are currently supported, a very rudimentary operating system identification. You can emulate specific devices based on the VID, PID, and REV for the different classes. You can fuzz that data based on the spec. So for example, if you've got a USB-based endpoint protection system, that's configured to only allow certain classes of device to be inserted. You can test the configuration of that using UMAP. You could also potentially circumvent it. So for example, if you know that only a certain vendor of USB device is allowed by the company, you can emulate one of those devices using UMAP. And so if the company had a whole bunch of those, but they didn't provide that one of those to you on the test, you can just be one of those devices. So you can comprehensively test USB host implementations. Okay, moving on to part 2 then. So as a result of fuzzing, earlier on in the year, I discovered a bug in Windows 8 in the RNDIS protocol. And it's a kernel pool overflow. It was patched quite a while ago, so there aren't any issues with me discussing the details now. So the RNDIS protocol is for allowing USB devices to talk via the host that they're connected to out to the internet. So it was actually on a TomTom device. I was using a sat-nav TomTom device, which when you plug it into a host, it goes off to try and find out if there's more map information available on the internet. And it uses this RNDIS protocol. So through mutation-based fuzzing, I discovered that there's a field within the configuration descriptor which talks about the number of interfaces. And if that number is actually greater than the actual number of interfaces, this kernel pool overflow occurs. So in the bug check, you can straight away see that it's pool related because you've got this pool block header size is corrupt message, which is nice and useful. And it tells us that it's within the function select configuration in that particular driver. So typical, probably unreadable IDA Pro bit of reverse engineering. Checking through in combination with WinDBG to try and work out exactly what's going on and what's where, and managed to pin it down to a point here where a null byte gets overwritten in an adjacent pool header. So further analysis using WinDBG. So if binum interfaces is 3, which is one more than it should be, so there's actually only 2 interfaces that are specified within the configuration, but we're telling it it's 3, and the number of endpoints is 2. That value there within the next pool header is changed from 10 hex to null, so it's been nulled out. We're overwriting the previous size element within the next NT pool header. Furthermore, notice that if you do one more than it should be with the binum interfaces and modify the number of endpoints value, you can actually decide where within that adjacent pool header you can overwrite with a null. So there's the structure of a pool header, and in the first example we were overwriting this previous size. In the second example we were overwriting, which one was it? Pool type, I think. So basically by manipulating these values within an interface descriptor, you can create, or you can write nulls in reasonably arbitrary places in adjacent pool headers. And here's a bit of pseudocode that explains what I think is going on. But essentially, it's not checking to see how many interfaces there actually are. It's trusting the value that's supplied within the protocol. So if you say, yes, there are 3 interfaces and there's only 2, the information that's gathered from them and constructed and then later used within the driver is bogus, and you end up overwriting that data. So this is Windows 8. I'm a hardware guy, an embedded systems guy, no reasonable amount about USB, but I'm certainly not a Windows internal exploitation expert. But having spoken to quite a few of the guys within the company that are, trying to exploit this on Windows 8 is very, very, very difficult. The number of exploit mitigation strategies that have been implemented by Microsoft in Windows 8, certainly around heat protection, around the kernel pool, would prevent me from doing anything particularly exciting as a result of being able to overwrite with nulls. Back in Windows 7, there are a number of strategies that I could follow that might make this exploitable, but Microsoft certainly considered it potentially exploitable enough to patch it. So, challenges that are faced when exploiting USB bugs. Well, apart from the exploit mitigation strategies that are employed by the OS vendor of the host, you've got a very restricted feedback channel. So it's not like you can trigger a bug and then get any information at all back via USB that will give you information about, addresses or useful information that might allow you to exploit any kind of memory corruption type vulnerabilities. The bug's often in kernel code, which, if you can exploit it, is great because it provides the possibility of privilege escalation, but also makes it quite difficult to exploit from a memory corruption exploitation perspective. The descriptors themselves, if you find a bug that can be triggered as a result of, let's say, some kind of buffer overflow, you're quite size constrained within your descriptors. So unless it's within the class specific information for which there's a bit more flexibility, that's something that makes your life quite difficult. As I mentioned, the typical impact is privilege escalation, and the exploit mitigation stuff I've also mentioned. One interesting thing that I've just started looking at, certainly with Windows, is the use of USB over RDP. So there's a bunch of specs that were developed by Microsoft to kind of extend USB remotely via an RDP session. And I find that quite interesting because if any of the bugs that I can trigger via USB can be communicated over that RDP session and then triggered remotely, it would then turn what is just a privilege escalation bug into a remote kernel bug. So seriously upping the ante. So some conclusions. There's lots of different ways in which these host systems deal with USB traffic, and therefore you can use the fact that there's different information for fingerprinting of OSs. The class-specific communications, even more revealing sometimes than just the enumeration stuff. Even vendors like Microsoft and others that have got a mature SCL process still have USB bugs. And I mentioned the huge attack surface here. I really don't think a lot of these USB host implementations have been rigorously tested. You can only go so far with static code analysis when you're reviewing these systems, and I think in the coming months using UMAP I'm going to identify a huge amount of additional vulnerabilities in some of these common implementations of USB. So you can potentially exploit USB bugs to provide privilege escalation, maybe even remote code execution if the RDP idea works, but it's extremely difficult to achieve reliably. Thank you very much. Does anyone have any questions? Yep.
So you're detecting Windows 8. Are you detecting Windows 8 against other Windows machines, like Windows 7, Windows 8?
Well, in the particular application, there's a slide that said application identification that talked about that Metro app. So you can tell the exact version of the class driver in that instance because within Windows 8, when you plug in a USB camera, it tries to modify one of the thumbnail images and it writes like a stamp of the exact version of the Windows 8 driver down to the build number, and that's specifically Windows 8. I think that there's much more scope for tying down very kind of granular information about these OS versions with the class-specific data rather than the enumeration phase. So especially when they're talking to applications kind of higher up the stack.
Did you ever try 32 or 64 byte?
I don't think I haven't noticed any specific differences between 64 and 32-bit versions of the OSs, but then I haven't specifically been looking for that, so that's something that I might. Any other questions?
Right here.
How much was Face Dancer?
So Face Dancer, up until relatively recently, you had to build yourself. You can buy the board. If you go to the Face Dancer website, which is in the slides, you can buy the board for about $5, I think, and then you have to buy all the different components, which comes to about, I think, $30. But there's a company called Zippiter now that are actually constructing them and selling them pre-built and also the firmware pre-flashed, which I can't remember the cost. It's something around $100, something like that, which makes life a lot easier if you're not very good at surface mount soldering, because it's quite complex to build if you're not used to that kind of construction. Any others? Okay. Thanks very much.